is, I don't know. Okay, so let's start. So let's start. There is a big pleasure to introduce Professor George Avalos from University of Nebraska-Lincoln. And he will speak about the problem of fluid structure interaction. And his title is Concerning the Strong and Uniform Decay of Solution to Coupled Fluid Multilayer Structure PDE Dynamics. So please.
Thank you. I very much appreciate the opportunity to speak in your seminar. This is work that I've undertaken in the last couple of years with Boris Muha at Zagreb and Pelin Geradelli. Well, she was a postdoc. She's in the States now at Iowa State University, a few hours from here. Yes, I see the word fluid here. For the purposes of this talk, replace word fluid with heat. We do have work with Stokes component, but I'm not going to talk about it today. In principle, everything I'm going to say, modulo and accounting for the pressure component is true with Stokes flow replacing the fluid thermal component. So the model, the geometry on which the model takes place is this geometry. Consider this cross section of a 3D body here, omega sub s, excuse me, omega sub f is a filled chamber. It encapsulates this structural component, omega sub s. Here, in omega sub s could be, you could take it to be a smooth body, but in applications, people have a mind to do computations. So almost by necessity, we have to it has to have some sort of structure with which you can compute with. So for the purposes of this talk, we'll take it to be polyhedral. The edges of the geometry here will be gamma sub f. Gamma sub s is the, of course, it's as it stands, it's the boundary interface between the flow dynamics and the structural dynamics. And of course, omega sub s being a polyhedral body, gamma sub s is a union. It's a union of polygonal faces. Okay. So with respect to this geometry, and of course, nu is the outward normal derivative outward with respect to the fluid component of the dynamics. And so with respect to this geometry, the model is as follows. Here, U satisfies on the fluid portion this thermal equation vector valued on the frontier of the geometry. U is 0. Since it's interacting with a structural component, it's not 0 on the boundary interface gamma sub s. Rather, instead, U has this matching of velocities. Here, this is a 2D velocity. This is a 3D velocity, where each sub hj on each polygonal face of the boundary, the polyhedral boundary, each polygonal face, h sub j satisfies this 2D, the skinny 2D or skinny system of elasticity. There's some matching continuity conditions in place. So for the purposes of this talk, if you don't want to play with indices this morning or this afternoon, and I can hardly blame you, you can think of hj as just one h formally across one contiguous interface gamma sub s. Okay. So one has the skinny system of elasticity with a forcing term being this difference of fluxes. U, as I said, is a thermal component. And here, this flux component comes from, is a flux relative to this 3D system of elasticity. Hence the buzzword multi-layered. One has this 3D system of elasticity coupled through matching velocities, and moreover through this difference of fluxes to the skinny system of elasticity. And both of these multi-layers are in turn coupled to this 3D thermal equation, each respective dynamics evolving on their own geometries. Cauchy data for time t equal to 0, the data of finite energy being pretty much what you would expect. L2 for the thermal component, H1 cross L2 for the thick and thin structural bodies, plus these continuity, plus these compatibility conditions coming from these matching of velocities, and of course from these continuity conditions. And here, these are the usual components of respective 2D and 3D systems of elasticity, their respective Lemay parameters. So this multi-layered system is very much in spirit, a bit of an extrapolation over the sort of single layered models, which have been much considered, at least from the point of view of PD control theory, over the last, 17 years or so. An initial work was considered in the famous French monograph of J.R. Lyon's, this exact model, and it was resurrected subsequently by Gunzberger and his collaborators with a view of computation. And since then, many people have looked at linear and nonlinear versions of this model. Our multi-layered interest comes from the fact that Boris Muha and his collaborators have considered using this model by way of mathematically describing the phenomena of blood transport in mammalian vascular structures. In the nature of things, these vascular structures are of composite type. The layers are composed of different materials, and with each respective layers having their own constitutive properties. Okay. So in a manner of speaking, this is like a biological analog of what one sees in civil engineering. If you Google like finite element and composite layers, you'll see paper after paper in various civil engineering journals to describe the mathematical modeling and numerical analysis of multi-layered structures as they appear in the material sciences. So this is one of a kind in essence. So some time ago, Boris and Pelin, my collaborators, and I looked at the matrix which models the spatial dynamics. Here, if you put this matrix together and specify a particular domain of definition, which you don't, if you don't mind, I'll beg off from describing, because it's a mess to write down. But the short of it is, it's smooth enough to ultimately give a meaning, point-wise notion of solutions to initial data in the domain of the generator, but not so smooth that we can't obtain semigroup well-posedness. And that is the result, namely that with the right domain of definition, there's contraction semigroup generation with respect to this matrix, which models the multi-layered structural fluid system. So the short of it is, given Cauchy data phi naught in the space of finite energy, one has a solution straight away for this linear problem by application of the semigroup. Capital phi sub t, of course, being the vector, the solution vector, which obtains the skinny and the thick structure components as well as the thermal component. Okay, so well-posedness is not an issue this morning or this afternoon. What is an issue is long time behavior. Looking at this model, two hyperbolic systems, each evolving in its own respective domain, coupled to this thermal component itself evolving in its own domain. If you multiply by suitable quantities integrate in time and space, you'll see that this dissipation, thermal dissipation, is propagated onto the entire 3D PDE system. So the short of it is this thermal dissipation propagates onto the whole so as to give this relation for the dynamics. Again, phi is the solution vector, which contains the skinny and the thick structural components and the thermal component. Okay, so given this dissipation of energy, it's not unreasonable to inquire after stability, and that's the point of our talk this afternoon. And so one facet of our talk this morning is a discussion of this result. We had in our aforesaid paper with Boris and Pelin, we did talk about strong decay with a more canonical model. Here we're talking about asymptotic decay with respect to the thick elastic thermal component. Namely, for initial data, for initial data finite energy, the corresponding solutions go to zero in long time. Okay, very basic statement. So here I didn't write down the domain of definition, but given it's enough to say here that the resolvent or the domain does not give rise to compactness. So there's you don't have any of these simple arguments so as to infer strong decay. I think the strong stability problem in the context of PDE control, it was like the first, PDE problem, I guess, from the early 1970s, say with boundary control of the wave equation, David Russell and many, many other people. The wave equation with Neumann or Dirichlet damping, the semi-group gives rise to a compact resolvent. So if you establish weak decay, then some invariance principles gives, or a clean invariance principle gives you that a compact resolvent gives you the deduction of strong decay. Here, the resolvent is not a compact operator. So this, this relatively simple argument does not apply here. Alternatively, there's the by now super well-known result of Wolfgang Arendt and Charles Batty, namely, if you have a semi-group, excuse me, if you have a semi-group, if there are no eigenvalues of the generator on the imaginary axis, and what's more, if you can keep track of the rest of the spectrum on the imaginary axis, in other words, if no more than countably many no more than countably many residual and continuous spectrum in the imaginary axis, then for a bounded semi-group, you have strong decay. Okay. Here in principle, probably with respect to our matrix of operators, in principle, probably we could have appealed to Arendt and Batty's result. But there's the issue of taking the adjoints, and whether you do things with one way or another, there are no free lunches. The sticking points are going to make their way no matter what path you choose. And I'll describe the sticking points with respect to this resolvent approach to strong decay vis-a-vis the spectral approach of Arendt and Batty, namely, if A generates a contraction semi-group, which moreover is completely non-unitary. And what we mean here, again, a term much bandied about in the 1970s, in the early days of PDE control, namely a continuous linear operator is completely non-unitary if the only non-trivial subspace on which the operator is measure preserving is just, there is no non-trivial subspace, okay, for which the operator is measure preserving. So assuming that the semi-group, contraction semi-group is completely non-unitary, then moreover, suppose you, well, for our purposes, the dense set is M. Suppose that for every point in the Hilbert space, you can establish a strong limit with respect to the resolvent, at least scaled by this beneficent power of alpha. If you can establish a strong limit, at least most of the time, for almost every beta, then the semi-group is strongly stable. Okay, there are various statements of this this resolvent, this strong resolvent, this resolvent criterion. We're using this one, and we'll see why in a bit. Okay, so most of the time one has to establish this strong limit, assuming, of course, that your semi-group is completely non-unitary. And so that's the initial task here. And again, we're falling very much in the line of what was done in the embryonic days of PD control theory. One has to obtain for uniform decay or strong decay, or whatever estimates have low order terms. These low order terms need to be removed. So what helps to remove these terms? Some compactness, uniqueness, argument, and argument by contradiction, which is supported by some uniqueness of the continuation. So of course, for the wave equation, of course, you have the classic Holmgren's theorem, originally from 1910, and of course, up to the late 90s, people were refining this result. I'm thinking of Lars Hormander and Tataru had a series of papers, between each other in the 90s, trying to restrict the necessity for trying to restrict the conditions on the coefficients of the principal part of the operator. For our case, our system of elasticity, we have the same consideration. So ultimately, to show that the semi-group is completely non-unitary, suppose consider a non-trivial space for which the semi-group is unitary, given our aforesaid dissipative relation. This gives, this gives straight away that the heat component is 0, and giving the matching fluxes, this tells us that the skinny velocity is 0, and the Dirichlet trace of the thick wave velocity is 0. And so mindlessly differentiating in time, we obtain that this flux term is 0. Why is this flux term 0? Because recall its appearance in the skinny wave, in the skinny elastic equation, is a forcing term. This guy is 0 since the temperature is 0, the skinny wave is 0. So upon differentiation, the flux of the velocity is 0. So given that the flux of the velocity is 0, then V, as defined here, satisfies this overdetermined system of elasticity. As I told you, for the wave equation, overdetermined wave equations give rise to the 0 solution. This is just Holmgren's. But for systems of elasticity, in PD control, as I told you, people beat the wave equation to death, boundary control thereof, and subsequently people turn their attention to systems of elasticity naturally enough. And so there are a lot of control papers, but a lot of them were incomplete insofar as the uniqueness component was missing. So some of their, it was a bit fuzzy, these details concerning removing lower order terms, but Matthias Eller, Viktor Isakov, Nakamura, and Daniel Tataru in a 1997 preprint, subsequently appearing a few years later in this French monograph, a journal compendium of seminar papers, that for boundary smooth enough, one has uniqueness of the continuation for the dynamic system of elasticity. As I told you, there were a lot of control papers. There were some control papers before this result. After this result appeared in 1997, there was like a cottage industry of control for systems of elasticity. The only issue here is, I think, there was an imposition of C4, I believe, smoothness on the boundary. So it doesn't quite, it doesn't apply for us since, of course, we're dealing with polyhedra. But subsequently, Matthias Seller and Daniel Tundikov, they they obtained the result. Yeah, the result was good. Was valid for piecewise smooth, which is good enough for our case. But Matthias tells me that that is actually it's true for Lipschitz. So actually, one has the system of elasticity, overdetermined systems of elasticity on Lipschitz, and ultimately, after doing some gymnastics and integrations by parts, one has that necessarily this subspace is trivial. So the multi-layered structure heat semigroup is completely non-unitary, and so we're free to use Yuri Tomilov's strong resolvent approach to strong stability. So in the course of showing strong stability, given that we're working on a polyhedron, we'll also need, I make no attempt here to give any sort of a completeness of results for systems of elasticities on irregular domains, just enough for our needs. And what our needs here are this: suppose Z, suppose Z satisfies this homogeneous boundary problem, the divergence of the stress tensor equal to right-hand side, square integrable. Then you don't recover H2 solutions, but for our purposes, you obtain good enough. And what is more, for our purposes, since of course we have coupling across a boundary interface, one can make sense of these flux terms at least on each polygonal face, which is good enough for us. The interior regularity, this was subtle, some in the early 90s. I'm thinking of Pierre Grisward's French monograph, and recovered that same year in greater generality by Nečas. For polyhedra, one has with zero boundary data at 3/2 plus epsilon. That's the best you can do. And of course, with boundary data, then it's a whole other matter, right? But at least on a polyhedron, we have what we want. So that's the interior regularity. And now to obtain needed control of the flux, it's essentially an exercise in linear algebra. On each polygonal face, get yourself an orthonormal system with respect to tangent and normal vectors. And just with your bare hands, so to speak, write out a linear system and solve it. And so you get the flux in right-hand side, where lambda and mu are the associated Lamé parameters with respect to the thick system of elasticity. And so, subsequently, you can appeal to estimate right-hand side. You can appeal to polyhedral Sobolev trace theory, which in essence is if you just want to recover boundary regularity on each polygonal face, then you have essentially the classical results of Sobolev trace theorem. Okay, if you take the union, of course, it's a whole other matter. But at least on each polygonal face, you're on very familiar ground. So right, so Z on the boundary gives me well definition of the normal derivative. And here I'm reading off from Monique Doche's little treatise on Sobolev spaces on polyhedra with her collaborators. And so with this extra regularity in tow, we proceed to tackle the problem. And the issue is ultimately, just as for uncoupled wave equations, the issue is estimating, dealing with the 3D wave and its interaction either with boundary data with other dynamics coming across the boundary interface. So to use, with that in mind, we're in position to try to use Tomilov's resolvent criterion. Recall, one has to establish this strong limit most of the time. And here we need this fine print most of the time, because you can't establish it all of the time from what I see, but most of the time is good enough. in particular, if we define this AD for Dirichlet, divergence of the stress tensor with the homogeneous boundary conditions, then when specifies this set S to be all real, all beta real, such that beta square is an eigenvalue. And so we'll establish this strong limit essentially on this complement, or all beta out of this set will establish the strong limit. So with this in mind, we just we consider our multi-layered structure thermal generator with a complex parameter. And so in spirit, you obtain essentially a Laplace or a dynamical system under Laplace transform, formally, of course. So we solve this resolvent equation with a given right-hand side. So formally under transform, our dynamic system looks like this. Our thermal equation, our skinny elastic equation with flux term is in part as a forcing term, matching continuity conditions with respect to the skinny elastic displacements, and our thick structural component, matching velocities under Laplace transform. And so we proceed to estimate this image or pre-image, the resolvent variable. So to this end, if phi denotes the, again, in the frequency domain, phi denotes the thick and thin structural components and the thermal components measured with the Hilbert space norm. Straight away, integration by parts, we obtain this relation. And so straight away, we have a static version of the dissipative relation. The right-hand side playing epsilon 1 over epsilon is essentially a good guy. Okay, so it's exactly a static analog of the thermal dissipative relation. And so given this control of the temperature, one has control of the matching velocities, the skinny velocity, the Dirichlet trace of the thick velocity. Now, the heart of the matter is to use a PD control theorist buzzword, to homogenize the problem. Let D for Dirichlet be this extension of boundary data extended in this way. You take a piece of boundary data, it's this image under D satisfies this homogeneous, this problem with homogeneous forcing term, and the given pre-image is boundary data. Given this underlying ellipticity, it's easy to use Lax-Milgram to obtain this regularity. And after the fact, one can use an energy method to make sense of the flux of these of such images with these in H-1/2 sense. So with this map D, we take our thick 3D component and subtract off this part, which essentially models the boundary data, so to speak. And so this variable Z, a fortiori, satisfies this divergence of stress tensor plus this complex plus this parameter equal to this mass's forcing term. But the material point is Z is 0 on the boundary. And so Z being on the boundary, we can ultimately make use of the aforesaid result of Griswold. But before that, using the fact that we're specifying that beta is in that set S, then beta squared's in the resolvent set, so we can apply the resolvent straight away and obtain this estimate in a lower norm. And now post-processing, we can obtain this estimate in the higher norm by putting this on right-hand side and estimating. And so we have a Z on the boundary in the higher norm, which is nice. But what we really need here is this, are these estimates for the fluxes on each polygonal face. And we'll proceed to use these fluxes. And now, given this regularity for Z, we can straight away recover the regularity, H1 regularity, the energy regularity for the thick component, the original thick component. And what's more, it's excuse me, and what's more, this estimate for the respective fluxes. Again, the flux of each homogeneous Z is well defined, as is the flux for this component D, the image under D, essentially integration by parts. And now we use this to estimate. So we're 2/3 of the way done. We have the thermal component accounted for. We have the thick component accounted for. Now we turn our attention to the skinny component. And here, this is semi-pedestrian. It's essentially an energy method. Estimate each skinny elastic equation by H and integrate by parts. So you have left-hand side here equal to right-hand side. And moreover, given the aforesaid continuity conditions on H, this term in the sum of terms just vanishes. And so we have this measurement, essentially a measurement of H in energy equal to right-hand side. So to deal with this, looking at the flux term, which we have control of, we have control of, we have control of the flux since we have control of the temperature. An energy method gives us an estimate for the flux in H -1/2. And of course, we have control straight early on of the temperature. We use this. So we have control of this guy. And as I said, we have control of these fluxes in negative Sobolev norm, which is more than good enough for our purposes. And so the short of it is we have control of the skinny wave equation. The resolvent for the velocity comes very quickly, again, using the resolvent relations. Right. W1 equal to right-hand side, for which we have control. Again, beta fixed. We're establishing the strong limit for fixed beta. We're looking at the strong decay problem only at this point. So for fixed beta, the short of it is we're in business because having control of this last component, we piece things together. And ultimately, we obtain this estimate of the necessary estimate to apply Yuri-Tomila's stability criterion, which recall right, this strong limit. So as it stands in the course, we obtain an estimate for this term, this image, with respect to a given point in the energy space. And so the short of it is, to conclude, we can scale the relation by any power of alpha, any positive power of alpha, not just 1/2, and we're done. So so the strong stability result is true enough, but given that we had a lot of wiggle room here, it led to the surmise that one can do considerably better than strong decay. So subsequently, we turned our attention to the issue of uniform decay, at least for strong solutions. So for the balance of my talk, we'll talk about the uniform decay, or more to the point, finding polynomial rates of decay for smooth data in the domain of the generator. And so to make, for the sake of explication, yeah, in writing down relations, instead of for the balance of the talk, instead of a divergence of stress tensor, just take the Laplacian, skinny Laplacian and the thick Laplacian. And also by way of drawing comparisons with the single layered model, which was, as I told you at the top of the talk, was has been looked at extensively. So the issue is, try to establish a polynomial rate of decay. Again, bear in mind, the only mechanism of dissipation comes from the thermal component. So one would think on the face of it, one's doing well just to conclude strong decay, because what are you asking for? You're asking for the thermal component, the dissipation coming from the thermal component, to leap across not just one domain, two domains, so as to influence two distinct, the behavior of two distinct hyperbolic dynamics. So in considering the uniform decay problem, if you should get it, you would guess that the decay rate might not be so great. Okay, and as you will see, that is exactly the case. And so, yeah, as I said, our result is with respect to a polyhedral domain, but as I said, I want to draw comparisons to what's been done with a single layered structure, fluid structure interaction. And this is the following model. Okay. This has been looked at, in structure, it looks pretty sweet and simple, but people have been looking at it. Yes, as I said initially, Joe Leonce in the mid 60s and up to 2016 or so. Well, I should take that back. And after Leon's monograph, there was a great lapse of time, but then Gunzberger in the early 2000s took a look at it, and then people seem to have jumped on these dynamics for a while. And so the issue is, one sees the thermal equation, just like our multi-layered system, a thick layer equation, just like our multi-layered system, but there's no skinny middleman in H, okay? So one has a matching of velocities, and one has the difference of fluxes is not the forcing term for the skinny wave equation. The difference of fluxes is just zero here for the single layer model. And as I said, the model in the analysis, the boundary interface was always smooth enough. So as I said, to repeat myself here, the single layer, a matching of fluxes. In the multi-layered case, the fluxes appears is a forcing term. Okay. But in either case, the heart of the matter in PD control theory, boundary control of the wave equation, for boundary control of the wave equation, one uses these time-honored wave identities of Kathleen Modowitz, subsequently used by Gung Chen, who really made the first substantial contribution in boundary control of the wave equations. He directly understood how Modowitz wave identities could be used. He used them by way of obtaining a very decent control of the 3D wave in L2 sense on the boundary. Okay. I'm sorry, L2 sense of the normal derivative of the wave, not the wave itself. Okay, that's not an issue. The normal derivative in L2 sense is an issue. And it's an issue here. And it was an issue for single layered equations. Okay. And our result in this connection, I'll give you the numerology at the end, but for multi-layered systems, one has this not very pleasant decay. It decays, but not terribly fast. And from what I see, how do you obtain a conclusion of sharpness? One has to have spectrality. One has to have an underlying spectrality so that you can cook up a spectral example. Here, we're pretty sure it's sharp, but until we have this spectral example in our hands, it's we can't say with absolute certainty that it's sharp. And so to obtain this polynomial decay rate, we use another result of Yuri Tomilov along with Borichev, which since I saw him presented in 2009, it's been used over and over and over. There was an earlier polynomial decay rate, I would say pluperfect, not sharp, but this of Lu and Bopeng Rao, but this is super clean. In essence, if you can control the resolvent of a presumably dissipative semigroup on the imaginary axis, bounded semigroup on the imaginary axis, if you can control the growth rate, well, if there is no growth rate, if you get a clean bound, then you have uniform decay, exponential decay for finite energy solutions. This is a result of Jan-Proust. Lacking that, if you can obtain at least this rate of decay with respect to the frequency domain parameter, at least for large values, then you obtain rational decay. And this resolvent estimate is tantamount to polynomial decay of smooth solutions. And so to this end, we look at the resolvent equation. Perhaps before I do this, I should say here our result is this nasty 1 over alpha star. In the single layered models, the result is a clean 1 over t, and that's it. But what allows for this, again, many papers, I would say the pluperfect result was by Thomas Ducart, who essentially used the result of Hormander combined with this iterative procedure of David Russell. So they got 1 over t plus a bit more epsilon. And to ultimately remove epsilon, Roberto Trigiani, Irena Lasieska, and myself, there was nothing for it but to invoke a pseudo-differential apparatus to the problem. Here, there's nothing for it in such a case but to take the boundary interface to be smooth. You consider the problem on the half space with a view of localizing and then micro-localizing the problem. You build these micro-localizers so that you can get your hands dirty on segments of time and space. And with respect to these pseudo-differential operators, which are very simple in structure, they're essentially a smoothing out of characteristic functions for all intents and purposes. But with respect to these symbols, you can cleanly get the result 1 over t. Now, that's because of what allowed for this pseudo-differential aside was the fact that you had purely a matching of fluxes. Now, if you wanted to work like a dog, for sure, you could micro-localize and then micro-localize the problem, but there'd be no point to it. This 2D elastic component gets in the way. I mean, here you have a second order operators in time and space. There's nothing clean to be had. So the result, the short of it is, this result is not going to be improved by any refinement, micro-local or a Hormander type refinement. And so in the bit of time, I'll try to tersely go over the main points of proof. Again, one considers the resolvent equation, formally the dynamic system of the multi-layered structure thermal equation under Laplace transform. And so again, we have our familiar looking dynamics. As I said, you have a control of the thermal component, and straight away, because of the matching of fluxes, one has this excuse me, one has control of the skinny velocity under Laplace transform, and the Dirichlet trace of the thick velocity. And just as in for strong stability, one has control of the flux term, good enough for our purposes, parameterized by beta. Again, you have to let beta run now. For the strong stability problem, beta, get yourself the desired estimate for fixed beta. You don't care about the other guys. Here, you have to consider what happens when beta's running, all right? To get the sharpest result, we obtain a refinement of Poincaré's inequality. Here, if you have control of the thermal component, then you have control of beta times this guy. Here we're improving by a scale of beta to the 1/2. And now by way of getting to the heart of the matter, again, the heart of the matter is L2 control of the normal derivative. By way of obtaining this normal control, we resurrect our Dirichlet map. In this case, a harmonic extension of boundary data for this canonical model. Homogenize the problem as before. So Z satisfies this messy forcing term with homogeneous boundary data. And we're using the fact that we can obtain a smooth enough solution. 3/2 plus epsilon would be good enough for our purposes. And now the point of it is, again, using the Sobolev trace theory for polyhedra given by Monique Dosch in her collaborators. Now we invoke essentially Kathleen Modowitz's identity for the wave equation, a static version. One can easily transfer time to a frequency domain. So in the frequency domain, this is exactly her identity, where M is any smooth enough multiplier. And so invoking Modowitz's identity and using the fact that Z vanishes on the boundary. Again, Z is the homogenized component. We have this relation. This holds for any vector field. And now, again, we're not working on a smooth interface necessity. It's polyhedral. So we can't talk about extending the normal vector, which is what's done for the smooth case. So instead, we use this particular vector field. In Griswold's book, he calls it an extension of the normal, but it's not really so. But it's it obeys this beneficent property. The smooth M gives you this good inequality, which gives you this initial control of the normal vector, which if you look at it, given that we're supposed to estimate the solution, i.e. phi, in terms of right-hand side times beta, you would say this result is essentially not terribly useful. Okay, the opposite of useful, but we'll use it's preliminary. We use this by way of obtaining a useful estimate in combination with our aforesaid control of a normal derivative in 1/2 sense, which again, this is true enough, but not terribly useful. We want L2 control of the normal derivative with right-hand side in terms of data, maybe penalize, where maybe one can penalize by epsilon at most. That's the headiest. We want the right-hand side. And so to do this, we control the skinny wave velocity by an energy measurement. Now we obtain the skinny wave energy measurement in terms of right-hand side. And now this puts us in a position to obtain, when I say appropriate, I mean an L2 sense with right-hand side that we can really use, okay? Up to now, estimates of the normal derivative, as it stands, we can't use these guys. So to this, we use the fact that the skinny wave equation has the difference of fluxes is a forcing term. So we rewrite brutally the normal derivative equal to right-hand side and proceed to estimate right-hand side. And again, there's nothing for it. One has to keep track of beta. Beta's not fixed. And so we obtain eventually an estimate for the homogenized thick wave in H-1 sense, which is not quite what we want, right? We don't want -1, we want 0, right? H0. So and now we use our bad estimate coming from Griswold's multiplier for the L2 estimate. We interpolate between this bad estimate and this good estimate, but the topology is too weak. So as to obtain this estimate in -1/2, which again is not quite what we want. So we use our estimate for the normal derivative in 1/2 sense coming from Sobolev trace theory on polyhedra. We interpolate again between 1/2 and -1/2 to get the desired control of the normal derivative. And as I said, the things, there's a sequel to the story, but this is essentially the issue, just as it is for unbounded control of wave equations. One has L2 control of the normal derivative of the thick wave. And so with a thick wave in your hands, you can obtain the homogenized wave energy, modulo epsilon, exactly what we want. Here is where the rough estimate, the bad decay estimate comes from. It comes exactly at this necessity of interpolation. We dehomogenize the problem so as to recover the same estimate for the thick layered variable component of the multi-layered structure thermal component. And now ultimately, of course, I'm going to end the talk here. But to finish the business, we obtain the control of the resolvent variable with right-hand side with beta running, with this parameter being 11/1/2, which gives the decay 1/t to the 2/11. Okay, I'll close the talk by saying, we have semi-analogous results with Stokes flow for single-layered structure Stokes flow, single-layered, no skinny structure component. Even strong decay and then uniform decay, there are spectral issues because of the pressure. For problems of this sort, for these coupled structure problems, it's not like uncoupled fluid flow. For uncoupled fluid flow, you have an associated pressure, which is unique modulo a constant. For these coupled structure problems with Stokes flow, you're not speaking about a pressure, you're talking about the pressure. There's no uniqueness modulo a constant, there's only uniqueness. And so because of this pressure variable, there's spectral issues. In particular, lambda equal to 0 is always an eigenvalue for single layered models. And that's the same thing here. Lambda equal to 0 is also an eigenvalue for Stokes multi-layered systems. But fortunately, the nullity of this 0 eigenspace is just 1. So at least you can characterize the null space very cleanly. It's the solution of an elliptic problem involving thick and thin variables. And so with the adjoint in hand, it's a pain to compute the adjoint. But computing the adjoint, you can work out on the orthogonal complement of this one-dimensional null space, you have strong decay. So we have strong decay to this point. Rational decay problem. Yeah, we're still working on it. Yeah, there are going to be unfortunately regularity issues with because of the necessity of using the polyhedron, but it's a work in progress. So I'll stop here and I thank you for your attention. Thanks again.
Thank you very much for your very interesting talk. So are there some questions or remarks? Yeah, please go on. Yeah, I think. Okay, so let me start. So so you mean by this Stokes flow that you have like stationary case or unstationary?
You say, oh, yeah, of course, the station, yeah. You mean dynamic Stokes flow?
Yeah.
Yes, dynamic Stokes flow. Yes.
Dynamic Stokes flow. And but then you need some coupling with structure.
Right. So the coupling mechanism is exactly the same. I'm sorry. Yes, the coupling almost the same. For the Stokes flow, you have a matching of fluid velocities with the skinny and the thick velocities. And now instead of difference of fluxes, you have the flux coming from the thick structure. And I guess you call it the Polya stress tensor, the flux of the fluid and the pressure times normal vector that appears, those three terms appear as a forcing term for the skinny elastic system.
And for this case, you also have some decay properties, this uniform decay, which you got.
Uniform decay, where modulo working out regularity issues, the answer is yes. But yeah, we need again, we need information on boundary regularity for solutions within homogeneous boundary conditions. So it's in this case with boundary conditions of mixed type with respect to the pressure. So it's a bit more delicate. But assuming that everything was like the smooth case, the answer would be yes. Okay, but polyhedral, one has to work out these issues. But in spirit, yes. But again, this is with respect to initial data that's in the orthogonal complement of the one-dimensional null space with for lambda equal to 0, because lambda equal to 0 is an eigenvalue for Stokes flow. Yeah.
Okay, so yeah, thank you very much. So are there some other questions or remarks? So please go on. Yeah, it seems to be not the case.
Okay.
Yeah, but anyway, it was really very nice and very interesting lecture, because somehow, at least in Prague, we are doing more, let's say, weak solution than strong. But anyway, I was already learning how to do strong solution and all this resolvent. So it is really different word and very, very interesting, I must say. Yeah, very complicated also. Yeah. So thank you really very much, Josh. Yeah, it was really pleasure to hear your lecture and your fantastic result. Yeah.
Thank you. Thank you for allowing me to speak in your wonderful seminar. I do appreciate it.
Yeah, thank you so much. Yeah. Okay, so I think this is the last seminar now for this semester. So what I wish you is a fantastic summer. And let me say that our seminar, which we will have another one on Tuesday, we will somehow continue still this week, let's say instead of Tuesday, Wednesday, and then we will try to keep somehow even working seminar, because we have some projects, so we cannot have holiday, we have to work. So, so at least 2 times per month we need to meet each other and exchange ideas. Yeah. So I wish you a nice day and see you soon in Brno, in Prague, somewhere, and so on. Yeah.
I'll see you in Brno.
Yeah. Bye-bye.
Bye-bye.